The first question today is going to be the most common question that we receive on the support desk for Whittle as of Whittle 2022 Refresh 3, and that is concerning the new Java issues that come up, the new Java errors when you first launch Whittle. In 2022 Refresh 3, we have decoupled Whittle from the Java runtime environments that we used to bundle with Whittle and install alongside. So now it will use the Java that is in your machine. This has the benefit of if your system is more locked down, then IT is able to more control your Java updates. It will update along with your system, and hopefully you won't get conflicts between the different versions of Java now that are required. The other side of that coin is that now we require a minimum level for Whittle to work. We test Whittle with a specific version, and then we expect that the computers that it will be installed on will have similar or more recent than that version. These error messages will look like this. This is the one that is most common, where Whittle requires Java 8 has been developed and tested with this version, specifically the Sumeru version of this, and it will give a link to download the file. These Java errors can come in some different flavors. However, they can look like these sort of Java language illegal access errors, a simple error loading program files jvm.dll, or this other Java language link error that's a little more convoluted, mentioned in the Yaneda engine that's in the background. So what all of these have in common is the solution. So first we will navigate to that Sumeru link, which is right here. So developer.ibm.com/languages/java/sumeru-runtime/downloads. Bit of a mouthful, but the link is in that error message. That first one is generated, and we on support are happy to provide the link as needed. We will change our version of Java in the second dropdown from Java 25 to Java 8. And in the error message, we specifically mentioned version 8-0-382. This is the version that we tested with and installed. Anything newer than that, such as the latest one, 8-0-462, should work, but I will be using 382 for the purpose of this demonstration, as that's the one that's mentioned. We scroll down until we find 8-0-382. We keep going. Here we go. And we find the version for Windows, and I have a 64-bit Windows machine. So I will use this row, and we want the Java runtime environment, and we want the MSI file. And you'll click on the blue MSI button here. This is the download link, not the SHA-256 below. That's a hash file and will not be usable for most users. So you'll download the MSI file. Once it is downloaded, run the installation file, and you will get a pop-up like this. Now, I already have it installed, so mine is going to look a little bit different, but if you have already installed and you need to fix it according to what I present in this video, by all means, you can do that, and yours will look exactly the same as mine. We'll click Next. I will click on Change, and we get to this tree. This is the goal that we want to get to. Now, the part that is overlooked a lot of the times when this is installed the first time is that there will be an option here concerning registry keys. Registry keys are how the programs know which version of Java to use when they boot up. They check the registry and they follow the links to those registry keys. So we want to make sure that this option, the one that says Java registry keys, will be installed on local hard drive. So I left click and then I left click again. If your option has 5, I believe there are some newer versions that have 5 options listed. It will probably be the 4th option. That will be the registry keys option. The other 2 that had Java home variable and whatever the 5th one is not important. We have found on support. So we'll click on that and we'll click Next, and then we will let it install and change the update. Mine is already working. As you saw, I have Java open, so I will not go through with it. But once you finish that update, you should be able to launch Whittle as expected. In some very rare cases, you will also have to reinstall Whittle after running that installation of Java. But I have found that in the majority of cases, you can just start running Whittle as is. Okay, the next topic we're going to be discussing is that of value mode. Now, Whittle is designed that you would import your block model with grade elements, then input all the prices and costs for mining, processing, the value of the material inside, etc. Whittle will determine the block value and then determine the optimal cut based on that calculated value. There has been a rise recently of users wanting to import their own block values and NSRs and other sort of values that bypass Whittle's calculation entirely. So I'm just going to walk you quickly through that. I'm going to do this in the Marvin model, but I'll minimize this so that we'll be working on a different block model. An import block model, it will be this below topo model.mdl. Hit next, we will import gold, density, rock type using element, density, and rock respectively. This is the bare minimum that you need for a Whittle project, a grade element, a rock type, and a density. We will also import value, and we will use the option on the list of block value. You can only have a single block value attribute. We'll hit next. The important thing with this is that it will not be multiplying that block value by the tonnage. It will be an aggregate value. And next, it will calculate the rock types. Our waste attribute we will import as rock, and other we will import as air. And then next, let this finish, and it will import. Now going through the list, it will import all our proper dimensions, and under formats, we get this checkbox at the bottom. This is often overlooked because it's kind of at the bottom of the screen on a tab that isn't visited terribly often other than when first importing. Check on value model based on block value. We'll rename that value to block value, which is the attribute that we mapped it to. We have to rerun this node, so we will do so. Under summary, it shows us our rock types and our grade element. It will not list our block value attribute there. We go to slope set. We're just going to use our default 45 degrees in all directions slope set for this. And we'll go to our pitch shell node. Now there's a couple of nuances here when setting it up. And the first one is in the mining tab with the reference mining cost. Now the documentation at the moment does state that you can use a value of 0 here. However, that is we are misspeaking in that, and it will be corrected in the next version of the documentation. You do have to put a value, but it could be a very low value. And I will just use 0.0001. This will create a additional cost in the model because it will cost that 100th of a cent per ton to mine, but it is rather negligible in all the experimenting that we've been doing. You can even go further to 4 zeros and a 1, so you're going to 1,000th of a cent per ton. However, I have not noticed much difference between the 100th of a cent to 1,000th of a cent in my given runs. You can put a different mining, dilution, and recovery, but part of the point of the value mode is that all this is being incorporated. It's really just that reference mining cost. You still have to put a value of some kind. I'll use none for my cost adjustment factors because those are, again, all included. Processing. At the top with the ore selection method, we will select value mode. This is the only time you will use this value mode option. And what this does is it allows you to create a path, because we still need somewhere for Whittle to put all of that mined ore to differentiate it from mining waste. But it allows us to put a processing cost of 0. We can also put a recovery if we want to, if we choose to. And what that will let us do is track the recovered amount of gold grams. This will not affect any sort of price or cost. Click on OK. We're going to leave it at 100% because this is a recovered gold attribute. However, if you wanted to put that recovery, you can. Now we use no cost adjustment factors here either. Under selling, we could leave this at 0 and 0. Our pricing cost is already rolled into our block value. In optimization, we can flex pseudoflow to make things faster. And we have to choose produce bench phases. The value mode option can only produce bench phases, not the nested pitch shells. So what this means is nested pitch shells, essentially it multiplies all the blocks by a revenue factor and then determines the optimal cut using whichever optimization method of that modified block value. Because we are importing a value of a block, instead we will be doing bench phases where we'll start at the top bench of the model, determine which blocks are inside of the pit, what is the optimal cut. Then it will look at the top 2 benches, bearing that in mind, and determine what is the optimal cut. And it will go down bench by bench to determine those values. It's very similar, but a different result. We'll go down to constraints. We can use constraints if we choose to. Expressions, user element. These are both exactly the same. Under the expressions tab, we do see at the bottom, however, user-defined block values. This is a way that you can still use Whittle's entered values, but write your own expression if you want to bypass it. This is a very, very, very rarely used option. Just because either you're going to use Whittle's calculation, which is the default mining calculation, or you're going to have your own calculation in your program. This is a middle ground that is just extremely rare. If you would like more information on this, please do contact your support department. We would be happy to walk you through how to write these expressions and what the variable names are. They're all located in the help files, but we're happy to help you with that. So you'll hit accept, and now we can run this node, and it should run very fast, and we will get an output that looks like this. So in this case, you see that each one, it only steps down by one bench at a time. So there will not be any giant increases in pit size where it goes from bench 5 to bench 20. Instead, it will go from for top bench, the next bench, and so on, and add material each time as it goes down. So that's the value mode. The benefits to this really are that you can have more complex expressions. I mean, the default mining expression is really just the processing, calculating the ore value. So that's price minus cost times grade times tons times recovery. And then if that is a positive, and then minus the mining cost. So this will be the mining cost is just the tons of material times the mining cost. And if it is positive, once you take into account both, you add them together, then it will be ore and it is processed. If it is negative, then it is not, and it is waste. That's just the default, a very simplistic calculation for some situations. If you have a more complex situation, you might want to model that in your GMP in SURPAC or in Datamine or whatever your GMP is, and then import that value into SURPAC for you to then calculate. And you can sort of mix and match as well. So if you want to do an NSR that doesn't factor in a mining cost, for instance, just want the processing value of the material because you have a very complicated processing structure, you can import that processing structure, add a reference mining cost here, and then Whittle will do that calculation for you. It'll subtract this reference mining cost, this mining cost value from the processed value that you imported, and then give you that output. So you can get a bit of a mix of the both worlds in this regard. Following on from our last topic, we're going to cover two questions that come up very often. They're very similar to each other, so I'm going to cover them at the same time pretty quickly. It's just the question of cutoff versus cash flow in the ore selection method, and in the schedule graph or the pit by pit graph, Milliwa, NPV versus balanced. Both of these follow a similar theme of Whittle giving you two choices and just what is the difference between them. So I'm going to start by moving back to the Marvin project up here and going to the pit shell node. Now, if we go to the processing tab, the reason I'm doing this is because it's multiple elements and multiple processing paths. I'm just going to add an additional path here, which I'm going to call heap specifically for MX for the purpose of this demonstration. So going on the list, I'm actually going to start from the bottom up. Profit mode is identical to cash flow mode, but specifically if you're using a stockpile and cutoff optimization node downstream, which looks like this. If you're not using a stockpile and cutoff optimization node, you will not be using profit mode. Value mode, as mentioned previously, is specifically for if you're doing a value model, if you imported a block value. If you are not doing a value model, then you will not be using value mode. So the choice is between cutoff and cash flow. There are two main differences between them that are worth discussing. The first is the question of priority. Cutoff is going to choose the first option on the list that is profitable. So for this MX material, for instance, there's a mill MX and a heap MX. Whittle is going to check mill MX, and if it is profitable, it is going to use mill MX. If it is not profitable, it will go down the list and check heap MX. So in that regard, you can prioritize. So if you want to prioritize material to the mill, even if the heap might give more value, if you just throw it onto the mill to begin with, onto the heap to begin with, it will prioritize the mill in this case. Cash flow will choose the one on the list that is the most profitable. So in this case, if heap is the most profitable, is more profitable than mill MX, even if mill MX gives positive value, it will choose heap MX. It will calculate the cash flows and choose the most profitable one. The second big difference is in the cutoff calculation. Cash flow uses a hard cutoff. The minimum grade that you put for each of the materials means that that material, that element, has to be above those cutoffs. So if I had a cutoff of 1 gram per ton for gold and 0.5 ounces per ton of copper, for instance, a block has to be above 1 gram per ton of gold and 0.5% metal, copper, for that block to be considered for this processing path. Otherwise, it's waste, regardless of what the block value actually is. Cutoff, on the other hand, creates a grade equivalency curve, demonstrated by this graph here. So we can see here the two materials, AU and CU, are similar to Q and P in this case. And having a cutoff of 1 and 0.5, for instance, it will create a cutoff curve where material in this gray area here is technically profitable, even though it is below the cutoff of both Q and P. So this material here will still be processed. So it's not a hard cutoff in the same sense. For cash flow, what it is doing is creating a hard cutoff in both directions, and only the material in this quadrant here that is above both cutoffs will be processed. So that is a big difference and a key difference for if you have a hard minimum that you need to account for. The way that you can handle this otherwise is by using stockpiling and stockpiling this material that is here for later use. But for the purpose of processing, it uses this sort of cutoff equivalency curve. You can affect which elements are used in this case using these checkboxes, and it will let you choose if an element is included or not in that cutoff equivalency curve. You'll notice that with cash flow, there is no such choice. It uses both elements or all elements every time for determining the block value. The second question that comes up, as mentioned, is if I go to the schedule graph, what is the difference between milliwatt NPV and milliwatt balanced? Wouldn't you always want to get the highest NPV possible from the schedule? And the answer to that is yes, you do in general want the highest NPV, but sometimes there's a physical constraint that is overlooked a little bit in those cases, which is understandable when you realize that Whittle will always stop its production after it hits one of the two limits. One of these limits, essentially, there's actually 5. There's 2 common ones, the mining limit and the processing limit. There's also the element limit and the processing group limit, so 4. If it hits any of these 4 limits, then the schedule then that schedule for that period stops and it goes to the next period. In the case of milliwatt NPV, it will hit your mining limit because it will keep mining more material to put into the stockpile, for instance. It'll keep mining more material to get some of that waste out of the way for a better year the next year and free up a lot of that high grade ore. And your processing limit might not get hit. It might not fill your mill every period. And for a lot of clients, a very hard restriction is that mill needs to be filled every year because it's costing money whether it has material going through it or not. And they don't have the option of just letting it idle and sit there. So as a result, milliwatt balanced will prioritize filling the mill and then maximizing NPV given that constraint. What blocks get pushed forward or not. And really the difference between milliwatt and fixed lead, just as an added question that does come up sometimes, is that fixed lead is our sort of baseline algorithm, which really handles the scheduling and determines how many levels down, how many benches down before it starts the next pushback. That's what the lead is. How many benches down before it starts the next pushback. Whereas with milliwatt balance and milliwatt NPV, you can have varied min and max leads to accommodate the fact that it can go down within a range before starting the next pushback. So that's fixed versus variable lead. The other big difference between them is mostly in waste management. I can't go too much into detail about milliwatt given it is proprietary algorithm, but what it does do is a lot of waste management, a lot of material management. How does it push waste blocks? How does it bring ore blocks forward back into the schedule so that you are processing the highest grade material you can the fastest? That sort of management techniques that fixed lead doesn't have all of that forward thinking. And NPV will prioritize the NPV regardless of what happens at the mill, and milliwatt balance will prioritize filling the mill and then meeting the NP and then trying to maximize that NPV. So both different approaches to get there. The difference really is just in that hard constraint of the mill and whether that is important. One question that has been gaining a lot of traction in Whittle and has a bit of misinformation surrounding it, and it's coming up more and more often, is the question of underground mining in Whittle. There is an underground mining option. You may have seen it earlier in the presentation, and I'll go through it again. But really, what does it do for the project? What are the results? What is the end? Can I schedule with it? What is it doing? To answer quickly, you cannot schedule with it. It will not produce anything in the schedule. Any blocks that it marks as underground blocks will be treated as waste in the reports and the results. And most likely what you will get is a smaller ultimate pit, if indeed there are blocks that should be mined underground. To help demonstrate this, I will be using this image here, which is from the help files, showing roughly what Whittle is doing in this case. There are three kinds of material in this situation: the black, the green, and the orange. Black material is material that is definitely going to be processed open pit. Orange material is going to be material that is definitely processed as underground. We already have, in fact, some levels here done in, so it is already part of an underground mine. Material that is green is the question mark material. Will this material be processed open pit, or is it more advantageous to create another level at the top of our underground mine to mine out that material as part of an underground mine? And when I use the word advantageous, that's what Whittle uses in the help files, and that's really how you can look at it. Is it more advantageous to mine a block as part of the pit or as part of the underground? This zone here is what the underground mining is considering, this oblong zone. And the red is going to be the optimum pit that is within that zone somewhere. It is not really designed to input the entire block model as open pit and underground option and let Whittle come up with the cutoff. It's assumed that you already have part of an open pit in mind, that you know there's a minimum extent that it will go to, or a maximum extent that you know that it's going to be part of your underground mine. And you really just want to look at the question mark material. It is recommended that you create an additional rock type for that material to treat it separately from the ore that is part of the open pit mine. Now, if you have 20 rock types, this can get a bit unwieldy, but that is the recommended for the optimum setup. To set it up, we will go into Whittle and we will go up to our pit shell node and go to our processing tab. Here we can create a processing path, and the checkbox for this is at the top right. Underground processing method. We're going to call this one UG, and we're going to apply this one specifically to OX. You can apply to all of them if you like. You can even click and shift to select if you'd like to select multiple at once. But we're just going to use OX for the demonstration. And now the question is processing cost. So because Whittle only has one box to enter a mining cost, and the mining cost is so different between open pit and underground, for an underground processing method, we also add the mining cost here. So as a result, this tends to be much higher than the processing cost of our other material that is being processed open pit, because this will then have the mining cost attached to it. This one does not. This is factoring in the mining cost already. So we do so. Because it is not using the information in the mining cost, that particular blocks mined and processed using the underground processing method will not use any of the positional cost adjustment factors that are used in this mining tab. So you have to factor all of those into this already. That's one of the reasons why it's recommended to have separate rock types for this method, so that you can factor those in a little bit more cleanly. Now, mining it underground is almost always more expensive than processing it open pit, mining and processing it open pit. Because when you look at the optimum pit, once you're already at that level, the cost of mining that block is relatively low. Whereas to do open pit, you generally have to do a whole bunch of infrastructure, build out a level, build out all your safety berms, all that sort of stuff that you need in there, your safety rooms, and get to that sub-level block, blasting it, mucking it. All of that is much more expensive underground than it is open pit. So as a result, this tends to be a lower block value when mined underground than you would get open pit. So the difference between that is the block value that Whittle will then use for its optimization. So the lower block value then cannot necessarily support as much waste on top of it on the sides and on top. So then you end up with a smaller pitch shell. If, however, that advantageous difference, the difference between the two, is still sufficient to mine out all the material, then you can end up with the same sized pitch shell, optimum pitch shell, that you would have had if you did not have an underground path. That's really all that Whittle is doing with this checkbox, is determining where that cutoff is, knowing that if it's mined underground, you still recoup quite a lot of the block value, just maybe not all of it, and you don't have to deal with all of this extra waste that's up here on the sides. And bear in mind, it would be in 3D, so quite a lot of additional waste you'd have to get to for your safety sides, for your slopes. The final question that will be looked at today is not a question that gets asked by itself very often, but is almost always asked as a secondary question for a host of other issues. And that is, how do I verify what Whittle is doing? How do I check the calculations? How do I know it's using my MCAF formula correctly? For that, we are going to be using the block value calculation node. So to find that node, you right click on your pitch shell node and go to add block value calculation. This node has two general functions. The first is to give it a list of block indices, and it will output the exact expression, the exact algorithm that Whittle uses to calculate that block value. The second is to create a value file for the entire model. This allows you to select from a host of different options, including the most common, which is just the block value that Whittle is calculating. And it will output these values for the entire block, every IJK block value. Or you can output block centroids, XYZ, or you can export as an MDL file and bring that directly into SURPAC. We'll delete that. You can also choose to apply the discounting factor. So by default, Whittle will do it at a revenue factor of 1.0 with none of your applied discounting factors. You can choose to apply them, and you can choose a different revenue factor. So if you want to see what the calculation is doing at a revenue factor of 0.7 or 1.2, you can just specify that here. Not every client uses 1.0 as the ultimate pitch shell. To find a block that is interesting for this purpose, what we will do is we will use the 3D visualizer. So we click on our pitch shell node, click the 3D visualizer, and it gives us a choice of options to view. This is actually going to be the first option if what you're looking for is whether it's calculating your mining cost adjustment factor or your processing cost adjustment factor correctly, which is usually the first tier of this kind of question. And if we use our visualizer, screen will pop up where we can select to show the pitch shell that gets generated, as well as a grid of XY values. So that's showing the grid of blocks on the plane. What we are going to do is go to our largest defined pitch shell, and we're going to change our block data to be gold, one of our elements. The goal here is to get a high grade block so that we can see a full expression in the results. You could also choose a high grade copper block. If you wanted to see your MCAF, you can hover over a block and it will show you at the bottom of the screen here what MCAF it's calculated for that block. Now, this block model, we're using an MCAF of 1, so that is what it shows there. But if you're using an expression, it will show you what it calculates. You can then locate that block in your mining program, see what all the different values are that go into that calculation, and figure out what Whittle is doing to get there, if it's calculating it correctly or not. What we are going to do is select AU, and we're going to find a high grade block. So this one seems pretty high grade. It has a gold element of 0.998, so almost at 1 gram per ton. And so we're going to mark down the block index. So that's going to be on the left-hand side of that row. And it will be 25, 35, 8. So knowing that now, we can close our 3D visualizer, go back to our new block value calculation node, go to blocks, and go to add. And we will add 25, 35, 8. You could add multiple if you want to see and compare different blocks, but for the purpose of this demonstration, we'll just do one. We will run this node. It runs very quickly because it's really just looking at that one block. And we'll go to the report tab. This report tab will now list, this is the entire calculation that Whittle does from beginning to end for that block. It will list all of your prices and costs that you enter, the details of the block, how many tons of dilution, recovery, all the element details, all that information that is used to then do the calculation later, including any cutoff that you might have. You'll see that it does calculate both the specified cutoff as well as the specified cutoff that will be the raised cutoff, and then the cutoff over is going to be Whittle's calculated cutoff value for this. It will use whichever one is higher. So starting at the top, what it will do is it will start with going parcel by parcel to show you the processing information. So Whittle will mine a block at the block size, but it will process a block at the parcel size. So we'll go parcel by parcel and show you the tons of the tons of that parcel. So 2650, what material it is, what number parcel it is on the list. The actual number of the parcel does not matter. Then it will show you the different methods that it's using. So in this case, there's only one method specified for each rock type. So it will show you method mill. It'll go through the calculation to show you, and there's a summary of what all of these different attribute names mean in the help files. If you search for how Whittle calculates a block value, it will show you what all of them mean. But most of them are pretty self-explanatory and able to be figured out from context clues. So revenue, available metal, minor recovery, price, revenue factor, element price conversion. Pretty straightforward. So what it will then do is find the value of processing that block. So this is going to be the positive value. And then it will go to the next parcel. And it's going to find all of them. And it will add that parcel revenue each time. So it's going to build up this parval to the block AG, which is going to be the block processing value. So that block AG is going to continually increase as it goes through each parcel that gets processed. If it was not a positive value, if this value at the end here was negative, then it would not process that block. When we get to the end of the parcel, so after it goes through all of the parcels, we'll get to the end of the block. It's fairly long because there are 27 parcels. It will take that block AG was the added value, the added positive value, and it will subtract block UG, which is the mining cost. So in this case, the mining cost will be 1.86 to the power of 6, which is quite a lot of cost, but it gives us our end block value. So in this way, if you have questions about how it's calculating a specific formula that's being applied, recovery, for instance, is a very popular one that has formulas applied, or price conversion. A lot of new users sometimes do incorrect unit conversions when they compare their block model formats tab here for element conversion to their selling price and cost unit conversions, for instance, and getting those to match with your imported model. And just checking the report here in the block value calculation node can really help to understand what Whittle is doing, how it's using all these numbers, and really where something might be going wrong. That combined with viewing of the 3D visualizer at both the pit shell level and the pit-by-pit graph level when it has been run is really the tricks that's used to debug what's going on with a Whittle project. How is it using your numbers? How is it calculating everything? If something is wrong, if my output was much too small, for instance, it's only outputting one pit, or it doesn't seem to like it's outputting any material at all, I can go to that 3D visualizer in the schedule graph, and I can see, or in the pit-by-pit graph, and I can see where that information is being used and how it's calculating those expressions.